Greetings to one and all. We, Team 2, is going to present on the topic Differential Thermal Analysis. The team members are Adnan Shirali, Amal A.S., Amal M. Shamir, Anlia S., Anna Joy, Anupama S., Arvind S. In this presentation, we'll go through an introduction, the principle, instrumentation, working, and applications of differential thermal analysis. Moving on to the introduction. Differential thermal analysis is a technique in which the difference in temperature between the sample and the reference material is monitored against time or temperature, while the temperature of the sample in a specified atmosphere is programmed.
Principle. In DTA, the material under study and an inert reference material, usually alumina, silicon carbide or glass beads, are heated under identical conditions at a constant rate. The difference in temperature delta T between the sample and reference is then plotted against temperature of the sample Ts, gives DTA curve or differential thermogram. Heat changes in the sample, either exothermic or endothermic, can be detected relative to the inert reference. Exothermic changes are represented by upward peak and endothermic represented by downward peak. Thus, a detail curve provides data on the transformations that have occurred without the change of mass but involving heat change. Example: crystal transition, glass transitions, crystallization, and melting. The area under a detail peak can be related to the enthalpy change of the process. Physical changes such as transition, fusion, vaporization, sublimation, etc. are endothermic. The chemical changes such as dehydration, decomposition, etc. are also endothermic, while oxidation in air, polymerization, etc. come under exothermic class. The upward peaks in the differential thermogram stands for exothermic changes, whereas downward peak stands for endothermic process. The peak area in detail is proportional to mass of the sample and enthalpy delta H of the physical or chemical change.
Instrumentation, furnace. The main function of furnace is to supply heat to both the sample and reference at the same rate. Sample holder. It is used to hold both the reference materials and the sample. The materials utilized to create the sample holder are both metallic, such as nickel, stainless steel, platinum and its alloys, and non-metallic, such as glass, vitrosilica, etc. Thermocouples. It permits the measurement of the temperature and furnace and that of the reference and sample. Then we have programmer. The furnace programmer is used to increase the temperature of the furnace at a steady rate. Then we have furnace temperature control system, a device that enables pure gas to keep the furnace and sample holders environment at an appropriate level. And lastly, we have DTA processor and recorder. Below we can see the block diagram of DTA apparatus and DTA thermogram.
Working of DTA. The furnace in DTA has two chambers. The sample is placed in one chamber and inert reference material like Al2O3 is placed in other chamber. The furnace is connected with temperature sensors. Then through an electrical source, heat is supplied to the furnace and the difference in temperature between the sample and the reference is continuously measured as a function of the reference sample temperature.
Applications of DTA. DTA gives information such as melting point, transition temperature of a crystalline substance, endothermic and exothermic process can be distinguished. Enthalpy change of process can be estimated by counting the peak areas. Characterization of polymers, study of decomposition temperature of inorganic solids. These are some of the applications of DTA.